This is a problem from your lab assignment, section 4.3. It says, consider a following function. Our function is f of x is equal to x to the fourth times e to the negative x. For part A, they want us to find the exact minimum and maximum values for f of x, where x is bigger than or equal to 0. So to find the local max and mins, we need to take the derivative, and so we take the derivative of the first times the second. So the derivative of the first, x to the fourth, is going to be 4x to the third times the second plus the first times the derivative of the second. So the derivative of e to the negative x is negative e to the negative x. After we find that, we're going to figure out where it's equal to 0 or undefined, find the critical points. It says here this is never undefined, and so it's equal to 0 when x is equal to 0. That's x is equal to 0. If you factor out an e to the negative x, and that'll never equal to 0. So if you set this equal to 0, that's equal to 0. If you set the second factor, the 4 minus x factor, equal to 0, you're going to get x is equal to positive 4 as your other critical point. Based on the graph, we see that f of 0, when you put 0 into f of x, we're going to get 0. And this is a local, what is it? A local, well, based on this graph over here, let's take a look at the factored form of this. If we put numbers that's less than 0, we're going to get a negative value, and a 4 minus a negative number is going to be a positive number, so that's going to be negative. It's going down. If we put a number bigger than 0, or between 0 and 4, let's say, then we're going to get a positive value for the first factor, x cubed, and then if you put a number here that's still less than negative 4, it's going to be positive, so it'll be going positive. So it goes from a negative to a positive. It's going to be decreasing and then increasing, so it's going to be concave. It's going to be concave, or it's going to be a local minimum. The next question, or the next part of this question, is asking us to figure out what f of 4 is. So we need to put 4 into this function. So if we put 4, let's just type 256, and then we're dividing by e, or we're multiplying by e to the fourth, and so that's the same thing as dividing by e to the fourth. So this is like 256 times e to the negative 4, or 256 divided by e to the positive fourth. And we know that if we put positive values in for x, that x to the third is positive, and this is going to go from putting values less than 4 here, will be going positive, and if you put values that are bigger than 4 in for x, it'll be negative. So a positive to a negative will result in a local maximum. So the exact minimum values is 0, exact maximum value is 256 divided by e to the fourth power. So now that we have the maximum and minimum values here, the next thing they ask us is to find exactly the values of x for which f is increasing most rapidly. And so increasing most rapidly, we have the first derivative given here, and so now we're going to have to take the derivative again, so take the second derivative. This is a triple product, and so the product rule can extend to a triple product rule, where we keep two of them the same and take the derivative of one piece and then just add on to it. So here, the first two factors, x cubed and e to the negative x, will stay the same, and they took the derivative of 4 minus x, that's negative 1. And so the next term will have 4 minus x, and then x cubed. Now we take the derivative of e to the negative x. That's going to be minus e to the negative x. And then last term over here, we have 4 minus x e to the negative x, and we need the derivative of this. This is going to be 3 times x squared, 3 times x to the second power, but we're also missing this factor of 4 minus x, so that's not accounted for here. So let's throw in the 4 minus x here as well. Boy, this is hard to do, huh? 4 minus x. Let's see if that worked out. There it goes. Okay, so let's check that. So that didn't work out so well. Let's see what we have missing here. Based on this, we have e to the negative x, so we need to take the derivative of this. Oh, I think they took that already. They had the x. They have a 4 minus x factored out here already, so let's take that out. 2, 3, 4, 5. Let's see if that took out. Yeah, so they took out the factor of 4 minus x. So it's a little tricky because you have to watch what they've taken out and what kinds of information they put here. And this is not normally the way I would do the product rule, but they do it a little bit differently, so we have to be flexible. Okay. Fortunately, they worked this out and they simplify it for us. This is our long-winded second derivative, but now if we get it simplified to this might be easier to deal with. Okay, so e to the x is never 0, so we won't worry about that. And then we want to know when this is equal to 0, and this is going to equal to 0 when x squared is equal to 0, and that means x is equal to 0, and they took the liberty of helping us out by factoring this second part over here. And so that factors out, and then we get x is equal to 2 and x is equal to 6. Find the value of x which f increases most rapidly. So increases most rapidly, that means our second derivative is going faster and faster, it's increasing. So we want to know when this is when this is positive, when it turns from positive to negative. And at x squared, it looks like it's just going to be bouncing off at 0. So when we put values, so fortunately we have this factored out for us. This is our long-winded second derivative, but our second derivative reduces to a factor that looks like this in factored form. We have e to the negative x, x squared, and x squared minus 8x plus 12. And now we're going to set this equal to 0 to find the possible inflection points, and those are also going to be the possible places where it increases the fastest and decreases the fastest, etc. And so e to the negative x will never be equal to 0, so the only way this is going to be equal to 0 is that if x squared is equal to 0, and x squared is equal to 0 when x is equal to 0, or when this quadratic is equal to 0, and fortunately they factored it for us and they found the solutions, x is equal to 2 and x is equal to 6. So it's going to be one of these values that's going to give us the fastest increase. So increases most rapidly, we have to look at where the interval where f increases. In part A, I think we found a local 0 is a local minimum and a local maximum at 4. So to the left of 4 it must be increasing, and then to the right of 4 is decreasing. So to the left of 4 it's increasing, and it has an inflection point at 2, so this is going to be the place where you're going to be increasing the most rapidly. After 4, it's going to decrease, and then here is probably the place where it's going to be decreasing the most rapidly. So they're asking us for the most rapid increase. The most rapid increase means that the first derivative is positive and the second derivative would be 0 going to a maximum. Okay, so let's submit that. This problem isn't looking for this, but I think this is one of those graphs that's worth graphing, or one of the functions worth graphing. So I took the graph already and graphed it, and we see the local minimum here at 0, and we see the local maximum here at 4. And then the other important parts of this is when x is equal to 2, we have the place where it's increasing the fastest. So imagine here it's going up, 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 it's increasing, and it's after it increases the fastest here, it slows down and increasing, but it's still increasing, but it's slowing down, and then it's going to decrease. So this is the graph. It's always good to look at the graph, and that's the end of the problem.